In the last video, I talked about the global usefulness test, or the overall F-test, for testing whether all the regression parameters b1, b2, all the way up to bk could be 0. Let's suppose that we've done that test and we've rejected the null hypothesis and concluded that at least one of the predictors, x1, x2, up to xk, is linearly related to y. Now we might ask the question, well, could a reduced model with less than k predictor variables actually be better than a complete k predictor model? And we touched on this briefly before when we talked about adjusted R-squared, and if you remember the shipping data example where we found that based on adjusted R-squared, a model with just 2 predictors actually was better than a model with all 4 predictors. So we've got the same kind of idea here. We're wondering if a model with less than k predictor variables is actually better than that complete k predictor model. And that happens if a subset of the x's provides no useful information about y beyond the information provided by the other x's. So for the shipping data example, this is because I think it was x2 and x4 provided no useful information about y beyond the information provided by x1 and x3. So just some notation here. RSSC measures the residual sum of squares for the complete k-predictor model, whereas RSSR represents the residual sum of squares for the reduced R-predictor model. Let's just pause for a second and ask ourselves which one of these two numbers will be larger. And the hint I'm giving there is to recall a geometric argument. So to think this through, let's imagine we have a reduced model, let's say with 2 predictors, and we got an RSS value, RSSR, and then we add 2 more predictors to make a 4 predictor model. Well, then RSSC will be a smaller number than RSSR, or at worst it's going to be the same, but generally it's going to be smaller. So the larger of these 2 numbers is this one, RSSR. Which model would be favored if RSSR was a lot larger? So that would imply that when we add the 2 predictors to our model, RSSC is a lot smaller. So that would be the case if the additional 2 predictors are really useful and are explaining variation in y beyond what can be explained by the original 2 predictors. So that means that the complete model would be favored. On the other hand, if RSSC was just a little bit smaller, so RSSR is just a little bit larger, then that would imply that those 2 additional predictors aren't really doing much, and we're better off with the simpler reduced model. Okay, so that brings us to the test. We're going to represent the reduced model with R predictors, so x1 all the way up to xr, and then the complete model is going to be the same all the way up to xr, but then it's going to have some additional predictors all the way up to xk. And our null hypothesis is going to look at those extra predictors and look at the parameters corresponding to those predictors, and it's going to say all of those additional parameters are equal to 0. And the alternative is that at least one of those parameters is not equal to 0. The nested F statistic is given by this formula, and the idea is that if this is a large number, it's going to be a large number if RSSR is a lot larger than RSSC, and that's going to allow us to reject the null hypothesis, and that means that we favor the complete model. On the other hand, if the nested F statistic is a small number, and that would happen if RSSR was just a little bit bigger than RSSC, then we won't be able to reject the null hypothesis, and we're going to favor the reduced model. We'll set our significance level 5%, and then we can either use the rejection region method by finding a critical value for an F distribution with k minus r numerator degrees of freedom and n minus k minus 1 denominator degrees of freedom. Alternatively, we can find the p-value as the tail area to the right of the F statistic for that F distribution. And if our F statistic is in the rejection region, or the p-value is less than the significance level, then we reject the null in favor of the alternative. Otherwise, we fail to reject the null hypothesis. Okay, and remember, rejecting the null in favor of the alternative means that we favor the complete model, whereas failing to reject the null hypothesis means we favor the reduced model. So let's look at this for the shipping department data. So I've summarized all the results here, and if I go back to R, I'll summarize the results in R as well. So this was the complete model with all 4 predictors, and then this one was the reduced model with just TWS and ASW. And I can use the results from those 2 models to calculate the F statistic. So the residual sum of squares for the reduced model is here, for the complete model is here, and then k is 4, r is 2, n is 20. So I plug all those numbers into my formula and I get 0.472. Alternatively, I can use the ANOVA function in R, and that gives me 0.472 directly. And then you can also see in this output there's the residual sum of squares for the reduced model, there's the residual sum of squares for the complete model. I can take the difference between those 2 residual sum of squares, 78.163, that's given here, and then I can put all the numbers into the formula to get my 0.472 here. Okay, so writing this out, here's my reduced model with just x1 and x3. Here's my complete model that adds x2 and x4. I'm testing whether b2 and b4 could be 0. And the alternative is that at least one of those 2 parameters is not 0. My F statistic is 0.472. We just calculated that. Significance level of 5%. A critical value, I can use R to find the critical value, 3.68. Alternatively, this is the code that you would use in Excel to find it. Or my p-value, I can use my pf function in R, and I get a p-value of 0.633, or here's the equivalent in Excel. So I'm getting an F statistic that's not in my rejection region, and I'm getting a p-value that's larger than my significance level. In other words, I cannot reject the null in favor of the alternative. In other words, neither x2 nor x4 appears to provide useful information about y beyond the information provided by x1 and x3. And that's the same conclusion that we had when we looked at adjusted R² for these 2 models, that the reduced model is superior to the complete model. So another way of thinking about this is that those 2 additional predictors are causing overfitting somehow. So why is this the case? Well, this is a model summary that displays information from both models. So here's, in the first row, it's the reduced model, in the second row it's the complete model, and I've also got adjusted R², which we looked at before, and we saw that that's higher for the reduced model than the complete model. We've also got the regression standard error S. That's smaller for the reduced model than the complete model, and that suggests our predictions are more accurate. And then what we just looked at was we got a high p-value when we did the nested F test, and that told us that the reduced model is favored. One final thing before I wrap up with this video is in R, if I fit the model, so this is the complete model here, and then I look at the analysis of variance table. This analysis of variance table uses something called sequential sums of squares, and I've called this model 1R because I've reordered the predictors so that here's x1 and x3, these are listed first, and there's x2 and x4. I've listed those last. And this sequential sum of squares ANOVA table, if I take the sequential sum of squares for PST after the first two predictors, and then for NUM after the first three predictors, if I add those two numbers together, so that's what I do here, 69.266 and 8.897, I get 78.163. Okay, I get the same number as I got when I took the difference between the residual sum of squares for the reduced model and the residual sum of squares for the complete model. And that's not a coincidence. That will always be the case if I look at sequential sums of squares and list the predictors that I'm testing, the ones that are in the complete model but they're not in the reduced model. If I add the sequential sum of squares values for those predictors, I'll get the same as if I take the difference between the residual sum of squares for the reduced and the complete models. So this gives you yet another way of calculating the F statistic. Okay, so that's the nested model F test. So now we've looked at, in the last video, a global usefulness test for all the regression parameters, B1, B2, all the way up to BK. In this video, we looked at a subset of the predictors, of the regression parameters, sorry. And in the next video, we'll look at testing regression parameters one at a time, or individually.